Hello and welcome to Nature Knowledge. This is a speaker series with experts sharing scientific knowledge on current issues affecting nature in Florida. I'm your host, Dr. Shelly Johnson, State Specialized Agent in Natural Resources with University of Florida IFAS Extension. Thanks for joining us today.
This talk is entitled Managing Aquatic Plants in Public Water Bodies. And this is going to be given by Dr. James Leary, who is an assistant professor in the Agronomy Department and also has an appointment with UF IFAS at the Center for Aquatic and Invasive Plants. So we're very appreciative for Dr. Leary joining us today and excited to hear about the topic. I'm going to let him take over from here.
Thank you very much for the introduction and again, the invitation to present to this audience. I'm very excited to be here this afternoon. Again, maybe a little bit of background about myself. Haley gave a nice introduction. I am an assistant professor at the University of Florida. I'm actually new faculty. I've been in Gainesville for 2 years now, and my specialty is in aquatic plant management. My prior appointment was in invasive plant management on terrestrial environments. So the aquatics of it introduces a whole other environment and arena for me where I'm learning more than I'm teaching. It's an amazing system to study on. And obviously I understand the effects of invasive species in Florida, 92%, and is an amazing number. And it's amazing that we are all informed on that. I saw a lot of 100% in there, as Haley had mentioned. My previous appointment was at the University of Hawaii. So I come from an area that is also very in tune with the impacts of invasive species. You guys like to call yourselves the invasive species capital of the world. We don't like it, but you have that dubious distinction. Well, the state of Hawaii does as well. And where we come from, the impacts are great. We have a lot of endangered species that are endemic to Hawaii that are not found anywhere else in the world. And so invasive species have a very immediate impact, direct impact on species extinctions that we're very familiar with. Here, things are just bigger, more aggressive. And again, you add water systems that cover 17% of the land mass in the state of Florida, and it adds a whole other dynamic to the situation. So I'm learning a lot about aquatic systems, and on my arrival in 2019, had a crash course in the politics of invasive species management in aquatic systems, where I had learned that one day after my start date, that the Florida Fish and Wildlife Conservation Commission was going to pause their aquatic plant management program due to the public outcry with the use of herbicides. And so that was eye-opening for me. Again, that was on my first day on the job to learn this. And so I quickly realized the social aspects of aquatic plant management and invasive species management, that it has a real effect on the ability to manage our natural resources. So today I'm going to give you my perspective of what I'm learning about Florida aquatic plant management, the effects of invasive species, and talk about some of the alternatives to herbicides. I'm not a proponent for one versus the other. This is not a talk about anti-herbicides or pro-harvesting or even anti-harvesting. It's really about identifying where we're at in the state of aquatic plant management, what we learned in the past, and why we make decisions now, so that we can become better informed and make the best decisions moving forward. So I'm going to talk about my research experience exploring operational performance of harvesting as an alternative to herbicides. And we're gonna jump right out of the frying pan into the fire and tackle one of the largest Hydrilla infestations in the state of Florida on Lake Tohopekaliga. I'd be remiss if I didn't acknowledge my colleagues who are contributors to this talk. Want to also acknowledge Andrew Howell, Rob Richardson from NC State. They're very gifted weed scientists. Also Ed Harris and Alex Dew of the Florida Fish and Wildlife Conservation Commission. So without further ado, why don't we carry on with the talk? And let's see, can you move? Yes, here we go. Sorry, I can't see because this thing is in the way. Move it out of my way. So managing invasive plants. Since 2008, the FWC has had the statutory mandate to manage invasive plants in Florida's public waters. They're responsible for protecting over 1.2 million acres of freshwater systems. That is a lot of area. Maintenance control is their modus operandi. It's their philosophy, and it's about coordinated effort to maintain low-level populations to mitigate risks. So what you're identifying, or what you should be recognizing here, is that this is not a program designed to eradicate invasive plants. Most of the invasive plants that have been introduced to Florida have been here for several decades, if not over a century. They are beyond the point of eradication to where it would be unsustainable economically and potentially have more environmental harm than the actual plant itself. So what FWC subscribes to is a maintenance control strategy to be environmentally sound and economically responsible. So some of the goals of maintenance control are to minimize environmental damage caused by invasive plants. That's number one. Conserve the uses and functions of Florida's public lakes, which have there is a multitude of uses, including recreational fishing, wildlife habitat, flood control, navigation. There are a lot of things going on in these lakes, and a lot of them conflicting with each other and and interfere with our ability to functionally control invasive plants. Regardless, we have to deal with them. They're a part of the heritage of Florida, our water bodies. We want to enhance the conditions for diverse native plant growth. We have a lot of exotic plants that are dominant and exclusive and choking out the native plants. And so that's a major driver. Again, that's kind of my background in Hawaii. It's all about protecting native species that were endangered and being impacted by invasive species. We want to learn how to use less herbicide in plant management, based on strategy and tactic, timing, and performance. And then that ultimately results in a lower management cost, more sustainability. When we think of sustainability, we're talking about environmental footprint, we're talking about economic value, and social acceptance. Can we get a consensus from a population of 20 million people that all agree that protecting our freshwater systems from invasive species is a responsible action conducted by a public agency? So finally, adapt management according to current conditions in each water body. There's over 8,000 lakes in the state of Florida, 1.2 million acres. That's a lot of territory. And as flat as Florida is, it is highly dynamic with climatic regions, and the geology of this state is really fascinating. Again, you're talking to someone who is new to Florida, so learning all these things is really fascinating to me. So let's talk a little bit about planning large-scale hydrilla control. First, let's talk about what hydrilla is. So hydrilla is a submerged aquatic vegetation, meaning it grows under the water column. It does not it reaches the surface, but does not grow above it. And that would be considered emergent vegetation. This is submersed. It is native to South Asia, was introduced as an ornamental species in the aquarium trade. I think we've heard this story before. For most of our invasive species, they tend to be attractive. They tend to grow abundantly. They're easy to propagate. These are criteria or life history traits of an invasive species. Hydrilla has them in spades. Hydrilla, again, from South Asia, is its native home range is tropical, subtropical environment. You come to Florida, there's a reason why Florida is attractive to people. It's also attractive to a lot of other organisms. Mild climate, year round. So what we find out is Hydrilla can actually grow in Florida conditions year round. There's no dormant period. So technically, from a biological standpoint, we have an opportunity to manage this species any time of the year. That's where we start. Okay, but there are other considerations based on the other services that these lakes provide, and of course the seasonality. So it is subtropical, but we also know that summers are monsoon, they're extremely high temperatures. And when you're talking about aquatic systems, you have to be in tune with that ecosystem, or you can make decisions that could have negative consequences. So some considerations for making management decisions on public lakes include high temperatures, which results in high biomass production. Now, what happens is if you control the plant, we know how to kill Hydrilla very easily, but if you have an abundance of vegetation in that water column and you kill it all at one time, that decomposition that occurs can stimulate the microorganisms that are respiring and suck the oxygen out of the water. That dissolved oxygen crash that could occur could lead to a fish kill, which if you're from here are familiar with, and that's something that we have to pay attention to. And the best way we can mitigate that from happening is we don't treat during the summer months when the temperatures are extremely high. So starting with treating any time of the year, we've already cut out 5 months out of the year when it's actively growing, but the consequences are so great that we try to minimize our management during this time of the year, strangely enough. Herbicides also degrade during that time. So if you're using a herbicide, they tend to break down faster. That's usually a good thing from an environmental standpoint. From an activity standpoint on plants, that can have negative consequences. Well, summertime is also when native plants are growing. And so if you're trying to get a selective treatment on the exotics, you want to try to treat and time it with when the exotic is dominant and the natives are in remission or in dormancy. Then you have hunting seasons, duck hunting, and fishing tournaments, world-class fishing tournaments. And then you have snail kite nesting, a native raptor that nests in these aquatic systems that are endangered. And so we have to be mindful of where their nesting sites are, and that impacts the decision-making with when you can control Hydrilla throughout the year. So here's so basically we're relegated to early spring and late fall as opportunities to treat. And that's the current practice now. So here we have a graph and a chart of an FWC budget and how they conduct maintenance control. So here we're talking about managing Hydrilla on a large lake. Lake Tahoe is over 18,000 acres. It's located in central Florida in Kissimmee. It's about 20 minutes south of Orlando. It currently has the largest Hydrilla infestation in Florida. There's probably close to over 100,000 acres of Hydrilla infestation across the state, and on well over 1,000 lakes. Most of those populations are less than 10 acres, interestingly enough. Toho is a different story. It's an 18,000 acre lake, and just this last year it was probably occupied, topped out with Hydrilla on at least over 50% of the lake. So we're talking about an infestation that is approaching 10,000 acres just on a single lake. So when we talk about maintenance control, it's very difficult to eradicate. And so we're looking at the graph here on the left. And this is a really nice history of Hydrilla, of the Hydrilla invasion. You've got this classic invasion curve where in the early 1980s, it was barely registered as being a species detected on the lake. And so this is what we call the lag phase. And then in late 80s and the early 90s, we had this explosive growth response where Hydrilla occupied over 75% of the weight. This is in short order. Within a decade, Hydrilla went from non-detectable to being uneradicable. So I mean, that is an amazing invasion phenomenon that is probably underreported. And so throughout the last quarter century, efforts have been to maintain Hydrilla at approximately 50%. And you can see the use of fluoridone, a herbicide treatment, and endothol, which is the current standard. And you can see it ebbs and flows. It cranks up to 75%. Management brings it down to 30%. It recovers up to 70%, brings it back down to 40. This is kind of the battle royale. This is Rocky versus Ivan Drago, man, and it's in perpetuity. And you can see the budget here. This is a 2018 budget for aquatic plant management by the FWC. It's a $17 million budget, and 10 million of it goes to Hydrilla Management, which is over 60% of the entire budget. So it dominates the decision-making of the regional biologists on protecting these lakes, and Hydrilla is number one by a mile. This second is floating plants, water lettuce and hyacinth, which are also extremely important invasive plants on our aquatic systems, but it pales in comparison to the Hydrilla management program. So I didn't do a lot of talk. I didn't talk enough about this graph here, but we talked about it from 1990 to 2000. The standard practice was the use of fluoridone, which is a herbicide. It's a whole lake treatment. The value of fluoridone was that you could treat with very small amounts in parts per billion and actually get really good selectivity. Hydrilla's Achilles heel was its sensitivity to fluoridone relative to the other native species. So you could selectively control Hydrilla and protect the natives. This is exactly what we're looking for in a herbicide treatment in natural areas. And it worked fantastically. It was really the gold standard. But it is by the year 2000, we had already recognized a resistance that Hydrilla was developing with fluoridone. So we really only got a decade of use out of this fantastic herbicide, which forced us to switch to an alternative, which is endothol, which was more expensive, less selective. And so we had to change our strategy. And that's in a nutshell, the brief history of Hydrilla management in Florida. But again, we're talking about the fluoridone resistance in short order from early 90s being the gold standard to by 2005, no use pattern established for any of the Kissimmee chain of lakes. This is an amazing event with the sad consequences. We lost in this deal, but we learned from it as we move forward. We're smarter for it now. We're very protective about how we use herbicides to prevent this from repeating itself historically. So the current standards for Hydrilla management are, we expect treatments that would typically provide 300 days of suppression. We are currently disproportionately reliant on endothol as the alternative. So again, where we've learned, we're also failing. We're also potentially repeating our failures. But we do have an abundance of other options that are effective but less adopted. And so this is the current use pattern. And so we're always at risk of losing another herbicide when we become over-reliant on its use patterns. Again, because endothol typically performs so much better than the others that this is, and because of the economics of it, this always seems to make sense as the best, as the preferred option in most of the situations. Well, this kind of comes back to another historical event. Again, in January 2019, this is when I started my position. This is how I'll always remember it. But this is also when the FWC put a 2-month moratorium on the use of herbicides. And as a result of the public outcry with the over-reliance on herbicides for aquatic plant management, And in response, they proceeded with public stakeholder listening sessions that took place throughout the state. I believe there was a total of 6 of them, and they collected responses and compiled them into a report. And from that report, they were able to establish an enhancement program as a response to the public's outcry for changing their practices in aquatic plant management. And they had quite a few items worth mentioning: expanding habitat management plans for individual lakes, forming a technical assistance group, including stakeholders who are on the lake regularly and have a personal invested interest in the protection of the environmental quality of the lake, learning how to use our herbicides better, improving the timing and the oversight of herbicide use. Also, there was a large demand for increasing the use of mechanical harvesting to manage aquatic plants. And this is going to segue into my program of studying this activity as a subsidiary to herbicide use. So let's move on. So I was tasked with re-examining mechanical harvesting for Hydrilla management. I say re-examine because there's actually a very extensive research history on the development and practice of using mechanical harvesters in aquatic systems. In fact, the technology is over a century old. We understand that harvesters can benefit a lake system by removing biomass from the water column. You see in the image here, this is your standard harvester design, where it has cutter bars in the front and a porous conveyor belt that brings up the vegetation and then drops it into a hopper, and you literally haul it off the site to a disposal area off the lake. And so there are a lot of benefits that come from that. In particular, you can remove tussocks, so you can improve navigation. You can also remove plant materials and tussocks that are banks of nutrients, and so you can actually reduce nutrient contents in lakes. It's not generally practiced because of the amount of material that would have to be removed to change the trophic state of the lake, but it could be in theory practiced. And in fact, most harvester operations in the state of Florida today are for tussock removal, which is not the same as removing hydrilla. So tussocks are, in brief, and I'm not very good at describing these, but in brief, are floating islands of vegetation, as you see here. They tend to have thick muck layers, but they're floating and they are emergent above the water line. So these harvesters can seek and eliminate these tussocks fairly efficiently with this type of equipment. Otherwise, there are very limited other options to do this kind of work. It's tailored very well to this demand. But the project mission for me is to figure out how this works in harvesting a submerged aquatic vegetation, plants that are growing in the water column. This is a different concept. In some ways, it's easier. In many other ways, it's harder. But my project mission in 2019 was to update mechanical harvesting, the technology upgrades for better precision in accounting, and with an objective to develop operational performance metrics on the mechanical harvest of hydrilla. How effective is this, and is it an economical alternative to herbicide use as it relates to the enhancement plan the FWC has established? So we set up an experiment on Lake Toho-Pecaliga, or Lake Toho, with establishing plots on 3 heavily infested areas that were 100 acres each, and then monitored harvesting over a 2-month period from June to August of 2019. You'll recall we're talking about the summer months when the plant is aggressively growing, typically not a preferred period of time to treat with an herbicide. So a bit of a novelty to challenge this technology in hydrilla management. So here we have a map on the right, and it shows the plots. We have a long rectangular piece in the North Cove of Lake Toho, and 2 square plots in the South Cove. What's also distinguishing about these is that the North Cove is very shallow. Average depths in this area are less than 4 feet, whereas the depths in the South Cove are deeper with average depths approximately 6 to 7 feet. So a substantial increase in water volume and elevation. These experiments were conducted with 6 kelpin harvesters with 3 tugs and airboats for transporting the materials to designated spoil islands on the shoreline. Kelpin harvesters are the largest class of harvester that we have in the state of Florida. They're 70 foot in length, 10 feet wide with cutter bars, and have a capacity of 80 cubic feet. These were deployed in June of 14 and terminated operations in August of 30. So a 77-day period where we were monitoring these operations. We were monitoring them with GPS tracking, and this is becoming a mature technology. GPS goes back, several decades, and this is a new use for installing GPS trackers on the boat so that we can see where those boats are operating and how fast they're operating at any time of the day. So this is an Internet of Things with GPS. It's feeding information into the cloud where I can literally monitor these boats at any time of the day in real time. And I also have access to all of the data. So these GPS are recording every 10 seconds, and you can see the point data being displayed in GIS. And you have 4 different boats here, and this is an abundance of information. So these are recording on 10-second intervals. And so you think about it, you have distance between points, and you have a time interval between those points, and that is a speed value that I can calculate in GIS to determine how fast these boats are moving. How fast can they cover an area? These are values that are pretty important if we're talking about the economics of a harvest operation as it relates to known costs for controlling hydrilla with an herbicide. So we want to know how much area can this boat cover besides the fact of how much can it actually remove. So this technology is proven to be indispensable for this type of study. We also monitor performance using hydroacoustic surveys. So fish finders, sonar with transducers on the boat that are recording not only the depth of bottom, you can see here is a profile that the acoustic data logger provides. You got the bottom of the lake, but you also see all of these strands here. This is Hydrilla here, and then you can see Hydrilla managed here, so it's much clearer. We can actually measure the biovolume of submerged aquatic vegetation using this passive technology. Very fascinating. This is new technology to me. I had no use for it in Hawaii, but extensively used in Florida. In fact, it was originally developed here. It is, again, an indispensable piece of technology for monitoring with a high level of accuracy the spatial and temporal patterns of management of hydrilla, not only suppression with the harvesters, but how fast it regrows from there. And we can get into this, but again, it's GPS anyways, gets technical, but we use geographical information systems for statistically analyzing the results of this data collected. And it produces a heat map that shows a color code where red equals hot, meaning there's a lot of hydrilla growth in here, and the blue means this is open water. So we can develop these kind of map presentations from this data provided from the acoustic sonar. We're also using satellite remote sensing. This is proving to be, again, a new technology. This is provided by the European Space Agency. This is the Sentinel satellite constellation. There's 2 satellites, and they circumvent the globe and repeat visits of Florida every 5 days. So you're talking about a high frequency intervention that produces an image of Florida, and here we have an image of Toho every 5 days at 10-meter resolution. So this is a pretty highly resolved image of of all the lakes in Florida, in this case, we're focusing on Lake Toho. It's also a multispectral instrument, meaning it has several bands of spectral wavelengths. The eye can see red, green, and blue. That's what your camera on your smartphone is. But we have red, green, and blue, plus 10 more bands of information on these satellites. And so this allows for us to do other calculations that using those bands, we can create algorithms that highlight the vegetation in the water body. And so what you'll see in this image, and we'll talk about this more, you can see some of the greenness in the water body. That's hydrilla growing in the water. So we can literally see hydrilla and floating plants and emergent vegetation in the water body with this satellite information. And here we talk about normalized difference vegetation index. That's literally a calculation for measuring the greenness of something. And so it's really about measuring the presence of plants. In this case, plants that are growing in aquatic systems, and in this case, hydrilla growing in Lake Toho. And so some of the parameters that you might want to remember as we get into some of the data, but I'll repeat it, is an NDVI value that is greater than 0 means that it's vegetated. Anything that is less than 0 means it's water. We don't have to worry about rocks and bare soil because that's terrestrial. We just need to know, is it greater than 0 or less than 0? And we'll look at some of the images, and so you can see what that means. Let's talk about some of the data. We have harvest efficiency and precision based on the GPS tracking. You can see the presentation of the data here, and you have some hot spots and cool spots showing where the harvesters were focused on harvesting hydrilla. All in all, not a very uniform or precise operation, a lot of uncoordinated management of these areas. Otherwise, fairly comprehensive. In total, we recorded over almost 1,500 harvest hours, where peak harvest operations were from 9 o'clock until 3 o'clock. You'll see here, you got operations. They were kicking off at about 7 and ramping up at 8 or 9 o'clock. But you notice that they tend to cut out at about 1 o'clock. Let's remember, this is the summer months of Florida, and lightning, thunder and lightning will chase you off the water. So that's another criteria. It's very difficult to get a full day on the water during the summer months. Harvesters need to be operating as many hours as they can. Herbicide treatments typically can be accomplished in 3 or 4 hours. So if you get started at 7 o'clock in the morning, you're typically done before those thunderstorms roll in. Harvesters need to be operating as long as they can. And typically we're getting shortened in the afternoon hours. Regardless, we also know from these GPS trackers that they were harvesting at rates of about 1.4 acres per boat hour. Okay, so this helps us understand how much area they can cover. These were at speeds at 0.5 to 1 meter per second, which I think I want to say it's about 3 or 4 miles an hour. Pardon me for not knowing the conversion. That's about right. What we also noticed too is these boats, they were harvesting, but they actually spent a lot of time idling. So idling comes in many forms. So first of all, at the start of the day, you're probably refueling, you're checking the oil, so you're doing a lot of things early to start the day. So there's a lot of this gray area here. There's a lot of loitering at the beginning of the day and at the end of the day. So that makes sense. So we're not going to penalize them for that. But otherwise, there's loitering throughout the day that they're doing something else besides harvesting. They maybe have a full load, and so they need to ferry this material to the barge so they can take it to the shoreline. They may have broken down, and so they have to do repairs. So that's another piece of the puzzle where it's not solid harvesting, continuous nonstop. There's a lot of activity. So you can see the breakdown where 30% of the time is spent idling, and whereas harvest is just a modest portion. And then you have the ferry time where speeds are going above 1.5 meters per second. So anyway, so this is how we can break it down with the information that's being generated. Harvest advocacy, we can see we have the north plot, that rectangular piece. This is from July until September. Remember, August 29th was the last day of harvesting. September was 1 month after harvesting, just for reference. You got north, then you got the 2 south plots. You can see in July, lots of red in there. From in the north plot, it goes from red to green, meaning it's check, but it's keeping it in check, but there's plenty of hydrilla in there. In August, the hydrilla is very abundant, and then it's even more abundant at the end. In other words, so this was a shallow plot, a lot of boat hours spent in there, very difficult to keep up with keeping it in check. So there was a lot of growth being measured. And then of course, recolonizing the plot 1 month after. So literally for 3 months of harvesting, you got 1 month of suppression post-harvest. Very difficult area to harvest in. So let's look at the other south plots. You can see pretty extensive hydrilla in here. You can see in August, we're starting to reduce. There's a reduction and peak performance on the last day of harvest. This is the best as we got, but there's obviously still a record of hydrilla in the water body with the acoustic profiles. And then as soon as we let our foot off the gas, you can see what happens. Look at all the hydrilla that comes out. So a lot. So this is again 1 month after the termination of the project. The temperatures from August to September, as anyone from here knows, are still very warm. We might as well consider September a part of summer. In fact, we might as well consider October and November a part of summer. Hydrilla grows very fast during this time of the year, and it really shows that harvesting is not a lethal management practice. It's sublethal. It's based, think of cutting the grass. When you're leaving stubble that's rooted into the sediment, it's going to regrow, and this is exactly what we're seeing. Similar with this plot on South 1, you can see we're keeping it suppressed when we're constantly harvesting, and as soon as we let our foot off the gas, it recovers. So here is, again, a box plot that demonstrates that effect. You can see South 1 and 2, and I'm going to be quick about this, but in August, you can see we got our best effects, the green bars showing a reduction. You can see the blue bars representing lake elevation, and we got the largest separation between the water level and hydrilla towards the end of the harvest period. This is the end of the harvest period, and you can see as soon as we end, the ramping up of the hydrilla biovolume in the water column approaching the water surface. Similarly here, you can see after harvest, here, this is the north plot, you can see lower lake levels, very difficult to manage the hydrilla. Here you can see it was topped out post-harvest. So that's really, in a nutshell, this is what we're dealing with is hydrilla's growth rates during the summer months outpacing our ability to cut and remove the materials at the same time. So here's some satellite images to kind of share the same depictions. At the top, you have the North Cove. So actually what we were measuring with the acoustics is telling us there's a lot of hydrilla in there. But you look at it from space, like, you know what though? Actually did a pretty good job. You can see where they actually cut out the surface growth of hydrilla, and it looks really clean from space. And you can see all the hydrilla growing around it. So, I mean, they certainly did something. This was not like not effective. It was in some ways very effective. That was on 8/22. That was the last week of harvesting. And you can see 2 months later, or I'm sorry, 6 weeks later on October 11th, you can see all the new green growth inside there. You can see all the hydrilla starting to recover. That's about as much suppression we could get during this time period. Similarly, in the south, you can see the square plots at the end of the harvest. This looks pretty nice, although I see something in here. I don't know what that is. Oh, sorry, going back. And then we look at 3 months later, in November, and you can see this plot has disappeared. This is probably related to something else, but you can see the outlines of this harvest plot, and you can see what was just a little bit here turned into a lot right here. So again, a highlight of the aggressive growth response of hydrilla to a sublethal suppression tactic. And so if we look at the NDVI, similar profiles as we did with the acoustics, you can see how it goes from clean, August, and then we get into post-management, post-management evaluations, September 26th, October completely filled in, and October by Halloween. So we, again, can actually, with the satellites, we can actually measure the term of suppression and how fast it was recovering in the plot. Similarly for South 2, mainly South 2, you can see had it really cleaned up in June and July and August. September, you can see it start to recover. And then October and November fully infested again. So clearly what we're doing is we're leaving half the material in the water column rooted in the sediment. We're allowing it to recover and reach back up to the water surface. And this is another box plot that demonstrates that, but I tell you, man, picture's worth 1,000 words. You guys can clearly see what's going on here, going from clean to reinfested in short order. And this is what these box plots say, the difference between the water column heights and the level of suppression with the greenness indice. So what does this all mean then? So what we're suggesting is in this one demonstration of the technology, the available technology, the current state of technology in harvesting, what can it do for us now? We're going to pause for 2 months. We're going to shut down herbicide operations. We're going to evaluate what our options are. These are the options we have available. Without herbicides, harvesting is a second place option. This is what we would have to adopt on large scale without the availability of herbicides to control invasive hydrilla. So let's consider what we know from the data that was collected in these demonstrations and apply it to a simulation of what would happen if harvesters were then the feature for maintenance control of hydrilla. So herbicide treatments we know cost from $400 to $1,000 an acre, where mechanical harvesting can be 2 to 3 times higher at approximately $1,900 an acre or $1,400 per hour, depending on how you write the contract. So we're talking from 400 to 1,000 to at least twice as much at 1,900. Excuse me. Summer growth is from June until November. It does slow down in December and January and February, and then picks back up in March. But from June to November, hydrilla is in it's enjoying life and is growing as fast as it can. So when we talk about summer growing season up north, it's 3 months out of the year. It's barely 100 days. In Florida, our summer growing season is 183 days. That means our management strategy has to account for 6 months out of the year minimum to be successful in managing this invasive species. So there's really no time off. You are constantly evaluating and preparing for the next management cycle. What we also know is that harvesters can operate about 1.5 acres an hour. And so when we do the numbers, that means if we're trying to manage 1 acre of hydrilla infestation over a 183-day period, and we know that we get about 30 to 60 days of suppression. Well, when we do the numbers, that means that each acre would require 5 to 9 boat hours for complete summer maintenance. For 183 days, each acre needs at least 5 hours to be successful. This would take approximately, for Lake Tahoe, on average, they're controlling about 3,500 acres of hydrilla a year just to keep it at 50%. This would take approximately 17 to 30,000 boat hours to manage these 3,500 acres. And so one boat can manage about 168 acres. So when we run the numbers, it would require a fleet of 21 kelpins 6 months out of the year just for this one lake. There are hundreds of other lakes that have hydrilla problems. And so really what we're talking about is if we were to revolutionize aquatic plant management with a focus on harvesting as a non-herbicide alternative, we have to be realistic about what goes into that. So I don't even think we have 21 harvesters in the state of Florida. And there are no kelpin harvesters anywhere else in the world. This is a technology developed for Florida's needs, and they're extremely invaluable. It's a resource that we're thankful to have, but we don't even have enough to manage one of the lakes. So we would have to build inventory on the industry side just to accommodate a transition into a non-herbicide harvesting strategy. The other one too is these harvesters are effectively living on the water. So there would be some infrastructure considerations on each of the lakes so that these boats are on the water constantly. These boats are moving pieces of equipment. They need constant maintenance. There's a cost factor with that. They depreciate. So now you get into the real economics of it. And these are realities that we have to consider if we're going to be serious about how we not only eliminate herbicides, how about just reducing the use of herbicides? My motto is we're gonna have to work harder to make it work. So that's what I have to offer. This is what I've learned in the 2 years of living in Florida about aquatic plant management and the dynamics of the technologies that are available, the fascinating technologies that are really telling a lot about what's going on. And some of the old technologies. How do harvesters work? They are still here. They are still valued in aquatic plant management. But we have to be serious about their considerations when we talk about the sustainability of an aquatic plant management program in Florida. This isn't like any other place. We're talking about a subtropical environment that is heavily impacted by invasive species. This is a huge demand, and it's a high cost system that it can only be managed properly by a public agency. And so it's inherent to know that we are always operating with limited budgets. We are not operating with unlimited resources where we should just build more harvesters and put docks up. And so I think everyone understands that, at least I hope they do. I think there's opportunities, but I think we need to be smart about it. I think we need to be cautious. We need to calculate accurately what the opportunities are. And from there, I think we have a bright future on how we can work with the aquatic plants that are in these systems and have healthy freshwater systems moving forward for our future generations. So I appreciate the opportunity to share my knowledge, my limited knowledge, and I hope there's time for questions. Haley, the podium is yours. Thank you.
Thank you so much for that very interesting talk. We actually do have quite a few questions in the chat box, and I'll go ahead and read them out to you.
Okay.
So the first one comes from Karen, and she mentioned, how much does management of invasive aquatic plants cost in Florida? And she saw your slide with the cost and then asked, is that budget for the entire state?
Yes, it is. So on average, so what I presented was 2018 numbers, so they're a bit dated, but over the last decade, the budget I recall has fluctuated between 15 to 20 million for aquatic plants. I think total is pushing about, I want to say 30 million, where half of it goes to terrestrial invasive plant management. I could be corrected on that. But yes, for aquatic plants, it's approximately 15 to 20 million. And as you can imagine, I think moving forward, we're very concerned about the pandemic and the economic consequences that probably are in our future. I don't think we've paid for this economically yet. So we're holding tight. I don't think we're going to see more money. We're going to have to make hard decisions on how we manage the aquatic systems in the near future.
Absolutely. Yeah. And it seemed, if I remember correctly, that the budget for Hydrilla alone was about $10 million, which seems
That's
like
right.
Quite a
It's over 60%.
Wow. Okay. Karen also asks, how much of the problem is due to nutrient pollution?
That's a great question. I think it has a lot to do with it. I think, again, I'm very fascinated by this. I'm very fascinated by the diversity and dynamics of Florida lakes. I'm read up a little bit on the trophic status of the lakes, the nitrogen and phosphorus levels in the algal contents that drive these trophic conditions. So you go from oligotrophic, which are low nutrient, low productivity, to hypereutrophic. So what's interesting is obviously plant growth requires nutrients. You would expect that extremely eutrophic conditions would enhance the invasion potential of macrophytes, in this case Hydrilla. You would expect higher nutrient contents would drive Hydrilla infestations. What I want to show you is, let's go back to, no, where am I? Oh, I don't have it, sorry. So let me kind of voice it out. Let's what I am hypothesizing, and what I'm also identifying, is you saw the graph that showed Hydrilla was barely detectable in the early 80s, and it was only in the 1990s when it exploded out of control. So here's another time period that some of you might be familiar with. In the late 70s and early 80s, the Environmental Protection Agency established the Clean Water Act, and Florida was a part of that, in that they set guidelines for reducing nutrient loads in the lake systems in the 60s and 70s. These were hyper eutrophic lakes, many of them, and a lot of them were green lakes, abundant with algae, and not a lot of macrophytes. It was in the 80s when we started to see, as a result of federal policy, nutrient levels were reducing, trophic states were declining, algae was on the decline, macrophytes were on the incline. You can see as clear as day, as algae's coming down, Hydrilla is exploding out of the water. It probably had a lot to do with nutrient availability, with loss of competition from algae. And I think light had a lot to do with it. So the interesting thing is, I think, and again, this is debatable, but I think the reduction in nutrients may have actually exacerbated or triggered the events that we're dealing with now with these macrophyte invasions. Yeah, it's theoretical, and certainly you could take a position on the other side to challenge me, but that's kind of what I'm learning.
No, that's super interesting. I think you're probably onto something there for sure. Before we go on to the next question, I'm going to go ahead and launch the poll. Dr. Leary and Michelle, you'll probably see it pop up on your screen. Just don't close it, and I'll go ahead and read the next question while it's up.
Okay.
So I'm going to go ahead and launch that. And if everyone would just respond to the poll, we'll keep answering questions during this. The next question comes from Chris Lockhart, and she asks, what was the pause in herbicides largely due to the concern about glyphosate?
So that's again, another good question. Kind of, sort of. So glyphosate obviously really stands out as the poster child for pesticides and the negativity associated with it. We understand that. I empathize with it. I have a very strong appreciation with glyphosate and its capabilities as a herbicide. I understand its environmental fate and the toxicological profile pretty well. I think it got lumped in with the pause just out of the general audience associates pesticide use with glyphosate and Roundup. But in reality, there is not very much glyphosate used in aquatic systems. It is not. So if all we did was eliminate the use of glyphosate, it would almost be negligible in impact. So I think it was misassociated, though I appreciate how it connects. But in reality, it is not very consequential to aquatic plant management in Florida.
sense. Mary Keith asks, is there anything that can be done, made with the harvested material? And she gave an example of cattle feed or garden compost.
Right, right. So this isn't new. In fact, there was a lot of work done in the 80s to study value-added product production of materials for hydrilla. So the obvious one is composted materials as a nutrient source for agricultural enterprises. That makes the most sense. The cost of shipping, transportation, manufacturing, and marketing generally doesn't pencil out. I mean, bagged soil just doesn't go for that much. You go to Home Depot and it's like $2. The plastic bag might be as much as the soil that goes in it, for instance. I don't mean to demean it. I think it's worth exploring, and it certainly has been. The obvious one that stands out is nutrients. Feed, I believe it does. It is palatable. Hydrilla is hard because it has very little cellulose, so it breaks down really fast. It's powder dry within an hour out of the water. Hyacinth is a little bit different. It's much more fibrous. It's lower to break down, so that is a potential. In general, I think we lose out on the marketing of it. Hence, in other words, people have thought about it for the last 30 years, trying to figure out how we can benefit from this as a resource. In general, though, I think economically, I think we need to be responsible in thinking about it as a waste product. How fast can we move this off the site into a stable location for the long term versus trying to figure out how to monetarily gain from it? That's where I think we start to lose out.
Yeah, definitely makes sense. Karen and Michael ask, are there any biological control agents available for Hydrilla?
There's one, and I'm going to get the name wrong. It's a moth, and it's a tip eater, and it doesn't seem to do that well in natural systems, but I'll tell you, it works really well in my mesocosm experiments. So I can't figure it out. Like, why don't you go out there? There's plenty of hydrilla in the lakes, but it kills my experiments a lot. So there is. But I think the better answer is there is not enough research that goes into biocontrol agents. To my understanding, ecologically, there's limitations due to the fact that we're now dealing with aquatic systems where there's an abundance of insect species in terrestrial environments available for testing. You have now limited that resource when you're dealing with aquatic systems in general. So the exploration is potentially a bottleneck for identifying candidates for biocontrol.
Karen also asks, where is the aquatic plant management funding coming from?
Oh, I was just thinking about this today. I'm probably going to get it wrong, and so we might have to do some fact checking on this. But to my understanding, so it's publicly funded, and I want to say that the funding for aquatic plant management comes from property taxes. I don't think it comes from licenses, fishing licenses and boat licenses. I could be wrong, but I think in this case, it actually does come from property tax.
I think that was all of the questions in the chat or on Facebook, but I actually have one for you. Actually,
okay.
I think I have two.
Those were great questions. Thank you, everybody.
Yes, absolutely. One interesting thing that I noticed was on the recovery slides that you showed, where you talked about kind of it being removed, but not from the kind of the substrate level. Right. What's the recovery time like for herbicide applications?
Well, that's a good question. So we talked about what we're getting with summer harvesting with summer harvesting is approximately 30 to 60 days. If we were to make treatments in August, September, at the same time, comparable time, then we would expect approximately 150 to 300 days of suppression with a highly effective treatment. Now, that would be the expectation, but it's not inconceivable that sometimes herbicides are difficult to make work, and so if it's a hot time of the year, some of the herbicide options that are used, especially enmethyl, are vulnerable to decomposition in the water. They have a short shelf life and they break down, which again is a good thing environmentally. You want it to break down to its elemental components, but it loses activity that way as well. And so we typically need exposure times at 24 to 72 hours in the water to get effective control. Well, some in the hottest conditions, it may only last in the water for 12 hours. So that's some of the challenge. But again, to go back to it, typically we're very educated on how to use herbicides and maximize their value. We expect at least 200 days of suppression for an effective treatment relative to the harvest operations.
Chris Lockhart asks, have you considered using harvesting through October and then a herbicide to knock it back farther, or like a hybrid approach?
Yeah, that's a great question. And that was kind of the next phase I was hoping we could get into. In some ways, the research got kind of fatigued, but it's a great question because it makes a lot of sense. It makes sense to consider the combinations. Do you get synergy when you can cut and then treat the stubble to eliminate those plants? The short answer is I think it would work very well. And your other point is well, what about harvesting, in later season? That's another great idea. So I think that we really challenged this harvesting technology at the worst time. We forced it into a situation where Hydrilla was rampantly growing. And so we saw the results where it was difficult to keep up with the growth rates. We couldn't harvest fast enough. You start to play with reduction in growth rates towards the end of the growing season and harvest it down that way. And I think you can increase the performance. That's great. And I should have worked that into the conclusion. That wasn't fair to you guys. So I'm glad you asked that question. Because then you can start to talk about, well, maybe 30 to 60 days turns into 60 to 120 days, or, so I mean, I think that's has value, and we're not there yet. I don't think we have enough experience with harvesters, at least experimentally, to say this is the perfect time of year, but we have enough institutional knowledge where that's common sense.
All right, well, I think I speak for everyone when I say that was a really fantastic talk, and I really appreciate you joining us. I think we're out of time at the moment.
Yeah.
But for everyone who's interested in this series, we will be hosting an expert every month. So please keep us follow along on our Facebook page and on our blog in the link that I sent in the chat earlier. So thank you for everyone for coming, and for, again, Dr. Leary, for you joining us.
Oh, thank you. The pleasure was mine. I'm very appreciative of this venue you guys offer, Haley. Thank you very much. This is a great opportunity. Please keep me on the active list. Next year we'll talk about something new.
For sure.
Excellent.